Greetings. I'm Robert Kennedy from the Institute for Interstellar Studies, US. And today I'm going to talk about the interstellar mission capacity of the human race between now and forever, based on some novel fusion fuel cycles. When we meet on Thursday, December 17th live, I will be accompanied by my co-author, Eric Hughes. I advise you, I'm going to be going through these slides very fast, but of course, since you'll be viewing them offline, you can pause the presentation at any point and look at a slide because there's a lot of information on them. They're very dense. So this work is based on a paper I wrote called the Interstellar Fusion Fuel Resource Base of the Solar System, inspired by William K. Hartman's work 40 years ago. It's in JBIS number 70, volume 71, number 8, is available as a handout with this talk on the SOCIA 20 website. So, what interstellar locations, what other stars would we want to go to in our neighborhood? Well, within 10 or 11 light years, there's two really good candidates, meaning good reasons to go, because they have a greater than zero probability of Earth-like worlds. That's Proxima Centauri, which happens to, as their name indicates, happens to be our closest neighbor. And Ross 128b, which may have a Earth-like world in the Goldilocks region. So discovering another Earth is certainly a compelling reason to go. Also, if we ever heard from anybody out there, that would be a compelling reason to go to. In a live session, I'll explain why just trading radio messages won't work. So how do we get there? Well, I laid out 3 basic broad classes of missions. The first class, class 1, are small probes from just a few grams to a kilogram to say about the size of a small car, all of which are pushed by power beams based on Earth or in near Earth orbit, pushing them out of the solar system at very high speed, 10 to 20% of C, and they cruise for decades and cruise by their target star without stopping. The next class would be machines, still uncrewed, but have their own engines. These would be rather large machines. One of them, as you see, is almost 1 kilometer long. The other one is about the size of an aircraft carrier, size and mass. These machines would mass tens of thousands of tons, get themselves up to 10% of C, and then at the destination, they could rendezvous. And finally, we have the idea of world ships or generation ships. And these are massive things. Note the 1 kilometer Firefly to scale in the bottom of the picture. So these things are kilometers in diameter, tens of kilometers long, massing billions of tons. They cruise at very low fractions of the speed of light, 1% of C or even 1/10 of 1% of C. So they would take centuries or millennia to get to their destination, even the nearest one, which is why they're called generation ships. Here's another concept of a giant world ship, 10 by 50 kilometers. This paper also is available as a handout download from the website. So what do these self-propelled starships run on? Well, fusion reactions, which here's a typical one. Deuterium on the left combining with tritium on the right, forming into a very tightly bound helium-4. And releasing a free neutron. Unfortunately, the neutron, being the lightest of the products, carries off most of the energy. and it sprays in every direction isotropically. Because a neutron has no charge, you can't do anything with it. So it passes right through stuff, doesn't bounce off stuff. You don't get any net thrust. So you're throwing away 3/4 of your energy with this useless neutron, hence the neutron problem. Why are we using fusion instead of fission? You know, atom bombs are well known. Well, here is the famous curve of binding energy. And on the far right, you split uranium into middleweight elements, yielding the amount of energy shown by the red arrow, unit energy per nucleon. When you take on the far left, take light elements, light hydrogen, heavy hydrogen, helium, or whatever, and fuse them into heavy helium or carbon, that liberates a lot more energy per unit mass. As you can see, the green arrow is much bigger than the red, which is why fusion energy will take us to the stars, but not fission energy. Now, here are all the fusion reactions, light fusion reactions, that the human race knows about. Perhaps more exist, but we just don't know about them yet. Of those, what are the ones we can actually use? Well, 2, maybe 3. So the green indicates the 2 that we can use. The yellow indicates the one that might be useful. And these ones with lines through them, either we don't know how to do it, like the reaction in our sun. We know how it works, but we can't possibly replicate it. Or in these middle ones, they're based on materials that fuels that just don't exist in nature. Or with the red lines, you know, we know how to make H bombs, but not engines, not something you can control. The reaction on the top, that's the classic deuterium DD reaction that everybody talks about. It's good, but it's got the neutron problem. At the bottom, you've got the proton plus boron 11 reaction, also known as the tri-alpha reaction, because it yields 3 alpha particles and no neutrons and quite a lot of energy. So that's outstanding. Now, how do those elements fit in? How, you know, what's their occurrence in the cosmos? Well, here's what we think is the occurrence of all the elements on the periodic table in the cosmos, periodic table, normalized to silicon. This is a logarithmic scale. So every unit on the scale here means either 10 times as common or 10 times as less common. So where do our fuels fit in? Well, first, I should tell you that this blue area on the far left of the region, these elements were created in the Big Bang. So that's hydrogen, helium, lithium, and the Big Bang stopped at lithium. And then in this large yellow area, all of these elements from carbon all the way on up to uranium are only created in the heart of stars during their life process or at the end of their life when they die and collapse, producing a nova or a supernova. Notice the gap in the middle. What's that? Well, that pink gap in the middle, that was made neither in the Big Bang nor in stars. And guess what? Our beloved boron sits in that gap. So boron is actually very rare in nature. If you follow the boron line across, you'll see it's about as rare as, you know, platinum or mercury or something. Further looking at this chart as fusion fuel candidates, you see boron 11, you see lithium 6, you see deuterium. Now, deuterium, we have loads of. We have 20 billion tons of it just here on Earth, all in the oceans. There's almost no helium-3 to speak of. For the boron 11, we have maybe 1 billion tons-ish total on Earth. And lithium 6, we have 2 to 3 orders of magnitude less lithium. So we're not going to talk further about lithium. We're going to concentrate on boron 11. You might say, well, why don't we just make boron or whatever? You can make elements. You can make light ones, as the Savannah River complex did, making tritium, but that costs $250,000 a gram. And you can make heavy elements through an extremely inefficient process, cooking them in a nuclear reactor. DOE sells californium for $25 million a gram. So aneutronic fuels like boron, they're so rare in nature, they're so hard to synthesize and so suited to interstellar missions that in the future, they're going to be extremely valuable to a starfaring civilization. So if we're not making boron, where can we find it? Right here on Earth. Why here? Because boron is, even though it is extremely rare in the cosmos, the Earth has hydrothermal activity, dissolves the boron out of deep rocks, and lays it on the surface where we do silly things like make laundry soap out of it. That only works on a terrestrial world that has plate tectonics and a hydrologic cycle. So neither Mercury, Venus, nor Mars are going to have this, nor any world beyond the snow line. Well, it's possible that asteroids or maybe a couple moons of Jupiter will have boron. So this is our patrimony of interstellar fuels. 1 billion tons of boron, an amount of lithium that's not worth mentioning, and that's it. That's all there is, folks. So the answer to our setup question, what's the interstellar mission capacity of the human race from now for forever? 30,000 one-way sorties out to say 10 light years. That's it for the rest of time. So how do we preserve this precious patrimony for the highest best use by posterity? Answer, we must forestall or avoid the temptation to waste this resource or use it prosaically for laundry soap or electricity generation by developing a substitute based on cheap, ubiquitous deuterium. And in that way, we can preserve the boron. We do have some examples from the past. In the 1800s, people were hunting whales almost to extinction to power lights for illumination at night because that was a very valuable purpose, but they almost wiped out the whales. Well, during the Civil War, the Confederacy wiped out the Union's entire whaling fleet. So that was pretty much the end of really large scale whaling. Happily, this was coincident with the discovery of the first petroleum well on Earth in Titusville, PA in 1859. So what was called rock oil supplanted whale oil. And that was off to the races. Here's another example from the past. In the Bronze Age, so 4,000 years ago, Mediterranean cultures and empires contended over just a few sources of tin, because tin plus copper makes bronze. Now, there's a fair bit of copper around, but tin is really, really rare. And in Eurasia, only 3 sources are known. And so there were fights. It was tin that made the Phoenician Empire. So you can say the syllogism is that the Bronze Age is to the interstellar age as a forest is to boron. Some of these cultures collapsed because they used up their wood supply with which they were smelting tin. So that concludes the talk with a conjecture that if the human race ever does detect somebody else's world ship, so a really big world ship, but it's running on boron, not deuterium, as opposed to a robotic probe, we'll know that they are either incredibly rich or really, really scared, or both. And I will take your questions on Thursday, December 17th. Thank you very much. And as a closing, my author is, co-author is partly responsible for this picture, Venus transiting over the sun. So that's it. See you on Thursday, the 17th.